Welcome back to the Electronics Inside, the show where we tear down tools, toys and appliances just to find out what's inside. I'm David, and in this episode we've been sent by the manufacturer Allpowers their S600 battery bank, or power plant. We'll talk about it. Before we get into it, really quickly I'm going to go through what we've been sent and what the features are, because I think that's going to inform what we find inside it. The unit itself comes with a little bag for all its ancillary cables. So I have, in my case, a UK plug to ICC13 power plug for charging off mains, and it will charge at, I think, 400 watts off mains. It also comes with these MC4, these nice waterproof single pole connectors, and an XT60, which ties into the solar cells. So along with the battery pack, they've also sent their 100 watt solar cells. And I was a little bit skeptical. I don't mind admitting that. So in theory, on the equator, a kilowatt of energy hits every square metre on Earth. An area 1 metre by 1 metre gets a kilowatt of energy from the sun hit it. Solar panels are about 20% efficient, there or thereabouts. So to get 200 watts out of that bit on the equator is about realistic. Now this is rated at 100 watts, and I don't live on the equator, and England, not known as the sunniest place on Earth. But I have had this plugged in and I have hit peaks of about 90 watts, so it's actually not doing too bad. It comes with its own little sort of kickstand, so it'll stand itself up, unfortunately only at one angle, and on the back it also has its own built-in little pocket with the connectors, the male-female C4 connectors, and a couple of other options including different battery connectors and barrel plugs, and the instructions sort of suggest you could charge your laptop straight off the PV cells. Sorry, I probably use PV cells and solar cells interchangeably. PV being photovoltaics is the correct way of saying you generate electricity from the sun. Solar cells could also mean solar hot water, something like that. But yeah, I don't know if I would be very happy charging something like my laptop directly off these PV cells. The fluctuating voltage, I mean the specification for these is something like 24 volts open circuit, and I think it was up to 6 amps closed circuit. I don't think I'd want to stick that in my laptop, but this does do a lovely job at charging the device. I will say at 100 watts of charging it would take 6 hours of perfect sunlight to get a full charge off a solar, but if you went camping for a few days and you were just topping it up each time, it's a good way to go. Battery pack itself. So on the top you have this wireless charging pad, so if you've got a wireless mobile phone all you have to do is drop it on top and it will charge. QI standard charging, Qi standard charging, I'm not sure how you say that other than QI. Pretty sure it's Qi standard wireless charging, up to 15 watts, which is decent. On this side, the C14 inlet for mains charging, you have the XT60 connectors, which go with that cable we saw a minute ago for charging off the PV cells, and you also have the thermal trip. So I'm a little bit interested to see whether that's thermal trip on the batteries, thermal trip on the inverter, what's getting hot that trips that out, or is it just a circuit breaker? We shall see. So on the front, you have a pair of USB Type-C which can deliver 100 watts each using power delivery. Power delivery, as far as I'm concerned, is a magical standard and everything should support it. We've got a couple of USB-A sockets which will do 18 watts apiece, which is a little bit of a weird rating. I don't know, I think I'm just used to it going in multiples of 5 volts. So 18 watts is, what, 3.5 amps-ish. It's got a couple of barrel jacks, which will be 12 volts at 10 amp. It's got that weird cigar lighter, car outlet adapter style, which again is going to be 12 volts. I'd always thought that was limited at 10 amps, but I've seen a few things sort of boast that they can do 120 watts. No, up to 150 watts using that connector type. So is that a hardware limitation or is that a fuse limitation in the car? If anybody knows what standard that connector should be and what the maximum current rating actually is, I'd love to know. head over to the Element 14 community and let me know down there. We've got a built-in LED light. I mean, it's lovely and bright. You don't want to be carrying this around as your torch, your flashlight, but I guess if you had this next to your campsite and you turned it on because it was there, maybe it's useful that way. And then you've got a little built-in display, which is lovely. It can tell you the power input and power output. It's lovely that you can switch different groups of outlets on and they will do different functions. I think that's a nice little touch, so you don't have to waste power running the inverter to get the AC power out of this if you only want DC out. And in my case, I've got what look like a couple of Euro modules with BS1386 outlets on them. I will admit to being very, very interested by this because we've got 3 prongs. So you've got phase, neutral, and a ground and earth. If you're generating electricity, it's probably good practice to earth your generator. But you can also treat it like an isolated power supply. But there are also other connections where you might tie the neutral and the earth together. I'm very interested to see which way they've gone with this, and I've read through the instructions and there is nothing in there saying only use double insulated products. If you're wondering, double insulated products are the ones with the 2 little squares inside each other on the instructions, and that means that they're sort of intrinsically safe and don't need the earth pin connected. And in UK plugs, you will often get them with a plastic earth pin. They don't say anything about mandating that. So the final feature we have on here is Bluetooth, which connects to their app, which gives you some very, very basic limited functionality unless you sign up with an account, which I didn't. I'm a little bit disappointed that you need an account to access something locally on Bluetooth. It's not like it's even hitting their servers. That's just then getting greedy with telemetry data, I'm afraid. It's available, it's an option. You can use it to switch on inputs on and off over Bluetooth if you want to. So let's briefly talk battery technology, because this uses lithium iron phosphate batteries, or LFP batteries, which is LiFePO4, if I remember rightly. You're probably familiar with lithium ion or traditional batteries that we have in sort of smartphones and laptops and things like that. And they are typically use a cathode material which gives them a certain characteristics. Now, the other battery that people may have come across is lithium polymer, which again uses a different cathode material, gives very different characteristics. They're all lithium-based chemistry, but lithium polymer gives a very high current discharge rate. Lithium iron phosphate is really good at doing a lot of cycles. Other battery technologies, if you really look after them, you will get up to 2,000 charges-ish on a life cycle. If you look after lithium iron phosphate batteries, you can get up to, in perfect conditions, 10,000 charges cycles, which makes them, for an application like this, really good. Let's get into it. So we've got a lot going on here. We've got sort of various charging styles, various output. We've got the battery controls, and they're all going to be something we haven't seen before. I should say, don't take things like this apart. The amount of energy contained within these batteries is a lot. This unit will take about 600 watt hours, I believe. This can output a peak of 1200 watts. So you could discharge this thing, in theory, in half an hour. I understand it's actually a peak output because it won't actually run that long. It normalizes down to 600 watts, which would be interesting to see what it would do if I plugged in like a 2 kilowatt fan heater or something. See how it does that. Does it brown out? Does it reduce the voltage, or does it trip? I'm also very interested by how good, what quality sine wave do we get out of this? It's quite common for things that invert, things that turn DC back into AC, to give a very poor quality sine wave, right down to essentially a 3-step square wave. So you get the 230 volts in UK is actually a root mean squared measurement, which means it's an average making all the peaks positive. The actual peak is, what is it, the times by the square root of 2 for this RMS reading to get to the peak voltage. And that means the peak voltage is actually something up there like 300 volts. And bad inverters will actually just go minus 300 odd volts, 0 volts, plus 300 odd volts. No smoothing, it's just a square 3-step process. And I'd be very interested to try and get a scope on this later and see how good the inverter is and what quality output we get. Aha! It's going to be very annoying if that last cable doesn't have a connector on it. Of course it doesn't. Okay, we'll kind of awkwardly balance that somewhere. Take these screws out, these alley plates. I have to admit, I kind of like the green hint to the mesh. It kind of reminds me of the Xbox. Okay, so now I've got the sides off, I can see that this is actually really modular and really nicely made. So, input side, AC input overload, that is only a circuit breaker, a 6 amp circuit breaker connected to that C14 input, which that makes sense. So it's 400 watt input. Actually, 6 amp is loads for 400 watts. Oh, I suppose this will take 100 amp. So up to 4 amp realistically for charging at 100 volts. So 6 amps a bit of headroom, but makes sense. So this must be the charging controller. And I'm really interested by this because we've got an XT30 on the output side, but we've got what appear to be a load of either power transistors or MOSFETs on a heatsink with a little fan. So this board is going to be what stabilizes the input voltage and current from the PV cells, which will fluctuate in voltage and current depending on how much sun's hitting them, etc. And that outputs something stable, which this can then plug into to actually charge the battery safely. So this board, I imagine, is something that they use in a lot of applications, but it's nice to know that they are properly managing this. They're just sort of hackily passing this onto the charging controller straight from the input of the PV cells. So this little board up here appears to be an off-the-shelf wireless charging controller. And the reason I say that is because it's still got a USB-C port on the inside. I really want to plug that into a USB-C and see if it charges, or whether that's for data, for flashing firmware or something to it. You just see 2 tiny little ceramic coated wires there labelled NTC, negative temperature coefficient. That's that little temperature sensor in the centre. Got a ferrite core and then the charging wires. It's just like our induction hob, but smaller and way less wattage. Just while I'm taking out this solar input controller, I just wanted to say how nice it is that the hinge and the handle has actually got metallic components, because it's not heavy, but it's not light. And the idea that you're carrying it on a purely plastic handle is a bit of a nightmare, but nice metal shaft. Yeah, I trust that. So these alley plates are maybe 2 mil thick, and I kind of feel like that's the sort of place where you could cheap down and just use self-tapping screws to sort of make a whole couple of threads is good enough. But no, they've actually gone to the lengths of bonding extra bushings on the back that they've got thread into. That's an easy place to cut corners, and they haven't. Okay. I'm pleased to see that the AC sockets do appear to have something with respect to grounding, or earthing at least. That is a lot of angry energy just looking to get out. So let's slide that over to one side and... So this is a nice little configuration. I wonder for a second if those Euro modules would pop out. Of course. There's always one. Cigarette lighter, the cigar lighter, that car 12 volt output is soldered on. And we should at least be able to pop this board over and have a look at the other side. I love this configuration with the LED, where they've sort of raised it up on a couple of 2.5mm pitch headers and put it on a daughter board. I assume that's partly for the optics, for the depth, for that focal length of the diode, but that probably also helps with heat isolation, because that LED will probably get very, very hot. You can see the size of the pad and all the vias on the back. Most of that's going to be working as like a heatsink inside. Interesting that that little lead I thought was the main power button. That's not. That's the backlight for the screen. A ribbon connector for the screen, and the buttons are just tactile switches. So this connector ran up to the wireless charging module, and this one connected up onto the solar regulation board. You've got the BXT60 down here, which brings all the power from the batteries onto this board. So I'm pleased to see on the AC side that there is actually something connected to the earth pins in the plug, so you don't have to use double insulated products, you can use grounded stuff. Still interested to see where it goes on the inverter side. Hopefully it will go through something resembling an RCD, residual current device, or a GFI if you're of the American persuasion. Especially in the scenarios where you would expect something like this to use, I think that's quite important. So let's put that to one side and bring the bomb over. The big obvious thing here is the 1, 2, 3, 4. In here we can see 16 3.2 nominal voltage, which is another difference of the LFE cells over lithium ion, 19.2 watt hours a piece, 32 700s, so that's 32 millimeters in diameter and 70 millimeters long. So what have we got sandwiched in here? So upright on its end here, we have got the charge controller, the BMS for these cells, and on top, up here, this is the inverter. Ooh, and possibly the rectifier too. Yes, looks like all of the AC, whether that's the input charging or the output to the sockets on the front, is handled by this board up here. So it's hardly surprising that takes a lot of energy. If you're wondering what I'm doing, there are 4 screws, or seemingly 4 screws, holding this battery tray, which holds most of the mass to the back shell. And to add insult to injury, the screws are also elasticed in to make sure they don't move. And I would love to be able to show you, but I can barely see what I'm doing anyway, so don't think you're going to get much of a better view than I am. Okay, I brought my overhead camera down a little bit to join me, give you a better view. Another good question. Does the earth from the output socket, which was that terminal there, come all the way through the inverter? Indeed it does. That is a dead short. Which raises an interesting question, because one of the modes of operation they propose for this in the instructions is running as a UPS. Now, a UPS is an uninterruptible power supply, and you would normally see them on mission critical infrastructure and equipment, and they can range from a little 600 watt type thing the size of a car battery up to room and facility size things with strings of traditionally lead acid batteries paired up to a giant inverter. And you talk about those in terms of autonomy. How long can they run their maximum load in the event of a mains power failure? Industrial UPSs are designed normally to look after computer systems, so they do what's called a double conversion. Double conversion UPS takes AC input, inverts it to DC, charges the batteries at all times, inverts from the batteries of the DC circuit back up to AC, and it's that AC that runs the mission critical equipment. Now, that's great. It provides, basically, if mains power fails, it's totally transparent at the point of use. The computers, the servers, whatever they are plugged into it, don't even know the power has changed because they're always being powered by an inverter. Absolutely fine. The trouble is that conversion process is pretty efficient, 90-95% efficient. But I've installed UPSs that are 160 kVA, 160 kilowatts in pairs to make sure that if one needs maintenance, the other one could go on. And bigger, 250 kVA. And they're not uncommon for buildings with data centers and things like that. When you get to full-scale data centers only, not just like a data room in a building, these things get bigger and bigger, and you can imagine losing 5 to 10% of that is quite significant. In that case, if you think your equipment is fault tolerant enough, you may consider, rather than using a double conversion UPS, I think they're called online standby UPSs. And I think that's how this works. So it takes the power in from the mains, charges the battery, but also allows the power to sort of passively transmit through the circuit. And it's only when the mains power fails that the inverter kicks in and does any work. And I'm making this assumption because in the instructions it says it will change over from in a power failure scenario in 10 microseconds, I think it is. I'll look it up in a minute. which tells me it's not a double conversion UPS. It's not inverting all the time. With the cover still on, because I don't trust this. Let's see if we can trace anything out. So that's the AC output for the sockets on the front. I'm actually going to test quickly, see if that theory holds. The fact that there is a change over time could be the time it takes for the inverter to start, but it could also be the time it takes for a pair of relays to switch over from mains to battery. No, that's off. So I strongly suspect those pair of relays down there, which are rated at 10 amp each, are what switch this from battery to mains throughput. But that's a really nice feature. So over here we've got a couple of power transistors, so they will be doing rectification. And over here we have 1, 2, 3, 4, 5, 6 output. So that makes me think this is the inverter output. And then you've got your normal array of capacitors for smoothing, your inductors for control. You'll have flyback transformers, because the input side of this will work just like a switch mode power supply, taking the AC input, providing high current output to the charging controller. And if you remember, this XT30 comes from the solar charging controller, and then you've got the XT60 coming from the rectification circuit. I feel like I'm saying rectifier and inverter a heck of a lot in this. That's all your AC power. Input, rectification, charge the battery. Output, which looks like it can be from an inverter, which is all this side, or it can be straight from the mains if those relays click over. So this little cable here is the DC output from the batteries. That's the one we measured at 26 volts. And that will go through that front panel and sort of provide your power delivery through USBs, your 12 volts. And all the power management for that is on that front board. That's DC to DC conversion, the power delivery control. That's cool. But this is also paralleled up with the input, which is actually kind of cool, because this goes back to what I was saying about using this as like an online UPS, online standby UPS, because the charging controller can choose to not charge the batteries, and you can essentially use that rectified power coming straight out of the rectifier. So you're not cycling your batteries, you're not adding to their life cycle. The charging controller can choose how it lets that cycle go, how low it discharges them, how high it discharges them, and monitor that voltage the whole time. That's awesome, actually. That's very cool. And like any multi-cell battery, we appear to have balancing ports to make sure that each cell is treated equally, and very, very big bus bars connecting all the batteries. Okay, so 26 divided by 8 is 3.25, which is about the nominal voltage for these cells. So I guess we have those 16 cells arranged in 2p, something like that. So 8 series, 2 parallel. On the whole, with this, I'm genuinely pleasantly surprised. The way the charging control works with the bypass and the AC throughput, it's the fact that you really genuinely could use this as an online standby UPS is kind of impressive. I hadn't expected that. And the variation of the outputs from the car cigarette charger to the power delivery on USB Type-C to the wireless charging, it's a good variation. And I would feel confident enough using this for most of its intended purposes. I'm still a little bit reserved on the earthing of the AC outputs when you're out in the field. But other than that, I'm quite impressed. If you've used another power generator, standby device, or whatever you want to call these, and you've got experience of how the different battery chemistry compares, I'd be very interested to know. Don't forget to let me know over at the Element 14 community. I hope you've enjoyed this one. Thank you so much for watching, and I'll see you next time.